going to guess that I'm live now. Lee hasn't given me a signal, but I get a thumbs up. There we go. Welcome to the ASV's July AstroTalk. Tonight we celebrate 100 years of the Astronomical Society of Victoria. Back on July the 5th, 1922, the ASV held its very first monthly meeting in a small room off the side of Flinders Street Station. So tonight we celebrate in style at the Athenaeum Theatre with 3 speakers. Tonight we'll be treated to 3 amazing presentations, the first by Dr. Sara Webb, followed by What's Up with Claire Kenyon, before hearing from Dr. Fred Watson. But before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. Tonight's stream is proudly sponsored by Skywatcher and Sidereal Trading. And remember, if you're enjoying tonight's stream on Facebook, you can donate stars, and those on YouTube can donate stickers. I've no idea what stickers are, but apparently they're donations. And if you're watching us for the first time, don't forget to like and subscribe and follow us on our Facebook and YouTube pages. Before we bring our special guests on stage tonight, though, I'd like to ask everyone to pay respect to members Neil Johnson and Rod Letts, who recently passed, with a minute's silence. Thank you for that. Now, I'd like to introduce Dr. Sara Webb. Sara is an astrophysicist and science communicator. She's always been fascinated by our very existence and the wonder of it all. Her journey to better understand the physics of the universe has guided her towards sharing this passion with the wider world. Sara's research has focused on observational transient astronomy. I still don't know what that is. Fueling a fascination for the unknown, she uses new and exciting machine learning techniques to help identify only the most interesting sources, hoping to uncover the rarest stellar activity and cosmic explosions in the universe. Sara is also a passionate science communicator and is dedicated to sharing the wonders of astronomy and astrophysics to a wide audience. She's presented on various national and international TV news programs, has regular segments on ABC Radio and Joy FM, and loves to present to the public, which is why she's doing her second presentation for the year for us. Now, on the topic, mysteries uncovered, 100 years of astronomy. Never have we known so much and so little about our universe than we do right now. In the past 100 years, we have uncovered a hidden universe. Sorry, damaging stuff up here, Sarah. One with dark matter and dark energy controlling our very existence. Explore the history of our understanding of dark energy and dark matter, as well as other cosmic conundrums. A lot can change in 100 years, and the last 100 have seen undoubtedly the most exciting discoveries in astronomical history. Sara, welcome to the stage.
Thank you so much for having me do my second talk. I love you guys so much, and I'm honoured to be part of the community and be able to share some of the most mysterious things that humans have ever experienced or understood. And we are very lucky to be in this time frame that we are. It really is remarkable. So before I begin, I'd also like to pay respects to the owners of the land where I work and where I live in the east of Melbourne, the Wurundjeri people of the East Kulin Nation, and pay our respects to the elders past, present and emerging. So this was the universe 100 years ago, and it's absolutely stunning. And you might argue that now we have less of a connection with the universe. We have sky pollution and cities, and you ask any kid who lives in the city, have you seen the Milky Way? And they might look a bit puzzled and maybe be a bit confused because this is no longer accessible really from where we live. And I think that's a real shame sometimes. I think we have lost the wonder of the universe when we don't see it as often. But 100 years ago, and many thousands of years before then, it was truly wondrous. Every night you saw the Milky Way and you could peer in and understand, or try ponder and understand, what was your existence? What is your meaning of life? What is the universe? It's a big question, and I still don't think we have an answer, but we have better answers now. So 100 years ago, we thought we were doing pretty good. When we break down physics and astronomy, we started to understand the Earth better than we ever had before. We had explored almost every corner of it. We started to understand what the Earth was made out of and everything that was chemical and biological. And, we thought we understood our place pretty well. We also understood our star. So for a long, long time, this giant ball of fire, not on fire, but this giant, what looked like fire, existed in the sky. And you can imagine thousands of years ago, that would have been very mysterious indeed. And then at night, it looked like there were little balls of fire. And it really wasn't until 100 and 150 years ago that we understood that these little sparkly little stars were all very different to each other. They were not all like the star. In fact, our star is on the rarer side. 7 to 8% of all stars in our galaxy are like our sun, and most of them are not like our sun and alone, so we really are special. But it wasn't until we started to understand that there were different sizes and shapes and temperatures and try break down what the physics was that was happening inside them. And all of a sudden, not only could you see the night sky and the Milky Way, but you could understand those stars a little bit better. The universe was making a lot more sense. And then we got to the era when we could record data. So the era of photographic plates was absolutely mind-boggling and changing, because no longer is there an astronomer looking through the telescope, making notes, making drawings, trying to do really complicated things without being able to record it. When we were able to record the data on photographic plates, it's like our world opened up, because not only could we see more of the universe when we had bigger and better telescopes, we could now do some detailed experimentation with the universe. And part of that was also looking at spectra. So again, we had broken down these stars. We knew that they were made of slightly different things, and we could understand them a little bit better than we ever had before. And the universe at this stage feels like it's making a lot of sense. It feels like we understand what stars are. We try to understand what our Earth is, and we're doing more science than ever before. And I thought I'd just highlight just how incredible it was to be an astronomer back then, because it really was a hands-on task. And I think, sadly, we're losing this now. Modern day astronomers rarely, I've observed many, many nights and never have I been right next to a telescope. It's always a room right next door. Never get to look through an eyepiece. That doesn't exist anymore, really. And you kind of lose that connection with the universe. And some of my research now, which I won't bore you about, but is trying to understand how are we changing the way we understand the universe through astronomical research when we're no longer hands-on. Because like Mark mentioned, most of my research is using machine learning, because we've got so much data now that you can't sit there, you can't be Annie sitting there counting spectral lines, figuring out what the stars are, and you can't be Edwin looking at the nearest galaxy and trying to figure out what's happening. It's just impossible with the amount of data that we have now. And with that comes a changing generation of astronomers, because you have them that have no longer worked with raw data from a telescope trying to understand it. And we don't know how that's going to affect the way we do science or what we look for. And I think that's quite interesting. So we're in the golden era, 100 years ago, when the previous members of ASV decided to make a society to chat about the wonders of the universe. These were the people who were really highlighting the universe. And I think a lot of the male figures we associate with astronomy and the golden era of astronomy, but I really wanted to highlight some of the female computational astronomers who, even though back in the time they weren't allowed to enter an observatory, which is absurd, some observatories didn't allow women to observe overnight until the late 1940s, early 50s, which is insane. It was counted as an improper place for a lady. I'm a lady, I've observed, it's not that exciting. But these women were incredible because they did all the hard yaks. The men would go and observe, collect the data. We would have the computers, most of them from the Harvard Smithsonian, who were doing the actual measurement and computation of this data that was then on photographic plates. And I like to see how far we've come. And then just highlighting that, these women who just 100 years ago, which is insane to think about, this would have almost been taboo. If you were to go to your community, go to your family and say, I'm not getting married, I'm going to study the stars. What a bizarre lady. And I'm very grateful that we have come so far that now I can be that bizarre lady and it be normal. But I think it's incredible that we've come so far and astronomy looks so incredibly different than it did back then. So back then, they had many big questions. Like I said, they thought they understood the universe as best as you could at the time. We were breaking down spectral types of stars and starting to figure out that maybe those nebula weren't quite in our galaxy yet. But we had some big questions, and I think we still have some really big questions, and hopefully we can answer a couple tonight. The first is, what is the universe? Good question. If anyone knows the answer, please feel free to tell me. I think we know more of what the universe is now, undoubtedly, and we'll cover that in a little bit. But we still ponder, why are we even here? Why is existence a thing? Why did the Big Bang happen? And I like to ponder, it could be because I like to catastrophize, but all of the things that had to have gone right for us to exist. It's really, really incredible. That leads on to, is Earth special? So we obviously live on a nice rock that's floating through space, and until not that long ago, we weren't sure if other planets existed outside of our solar system. And certainly in our own solar system, we're pretty sure Earth is the only one that has everything that we need for life. Maybe we can find something else under a moon in the future years, under an icy moon, but until then, it's looking like Earth is pretty special. And then finally, are we alone? I think that's always a huge one to ponder. And I think people have been doing that for many of thousands of years, is if this is the universe, no matter what you could see of it, it's pretty remarkable if it's just us. So hopefully we can answer those questions today. And we'll start with the easier one, maybe. What is the universe? So if you were to ask people hundreds, thousands of years ago to break down what the universe was, you'd get some incredibly creative solutions to what was happening. And again, it is very confusing, especially without the use of telescopes to actually understand what is happening. But I think what's remarkable is this idea of we were always special. We always thought we were special, whether we're at the center of the universe or not. We know we're not at the moment, definitely not. But I think it's amazing that we tried to define what we were seeing, stars, our sun, the Milky Way. We tried to interpret that with our beliefs at the time. So maybe it's spiritual beliefs, maybe it's just superstitions. And you get all of these magical things where you get, the 9 layers of heaven and hell are up there somewhere. We've had a good look. I don't know if they're up there. But you'd also get things like the luminous ether. That was a good suggestion for what the universe might have been back in the time, because we saw this light traveling from stars and we wondered, how is that possible? In Earth, we have air, we know that, and we thought we needed a medium for something to travel through. We now know that is not the case. But back then, that was our best guess at what the universe was. Maybe it was layers, maybe we had an ether, but we didn't know where we came from or where we were going. And again, just another incredible illustration of trying to make sense of what we were seeing. Hundreds of years ago, there were planets, stars. How do you make sense of that? And I think really only in the last 100 years, do we have more of a picture of where we are in the universe and what we are in the universe in regards to everything else? Are we special? Maybe not. But I think it's remarkable to look back on. Another of my favorite things is trying to figure out what we were made out of. So this is not necessarily astronomy, but definitely relates, is what was the universe made out of? And of course, there's the classic earth, wind, fire, water. And this seemed okay for a while until you broke something down and you never got to any one of those elements. Say you're working with molecules or rocks or whatever it might be. You could never find a single element. Didn't make a lot of sense. But that was our best guess of maybe what the universe was. Obviously, hundreds of years ago, hundreds and hundreds now. But I think it's a testament to humans, our inherent desire to try understand the universe, the earth, and ourselves. And if you're interested in old history like this, there's actually a book called The Anatomy of Melancholy. I think it was from 16 something, and it is trying to break down the human body and why do we get sad. And it's a fascinating book because instead of these 4 elements, you now have 4 humours in your body, which we now know obviously not the case. But again, a testament to just us trying to understand what life was and what we were. Of course, we started to understand that things were not made of earth, wind, fire, and water. They were made of atoms. And we really didn't have a great model of the atom until Rutherford came along and got a more accurate representation of what an atom was, the fact that we had some positive, some negative charge. But even then, all the way back when Einstein is writing his photoelectric effect or his gravitational, the theory of general relativity, we didn't understand that we could break atoms down all the way down into subatomic particles and quarks and fermions. No idea. The standard model didn't really exist yet. But with our understanding now, a lot of things come into play. One of them is obviously electromagnetic waves. This is light. This is every wavelength of light you can think of. And this is how we see and interact with the world most of the time. And it's how we traditionally we're seeing and interacting with the universe. And it started to make a lot more sense when we started to understand that light acted as a wave, acted as a particle, and we could use it to manipulate things so we could understand energy levels of atoms. So it's all coming full circle. And all of a sudden, our stars and what we were seeing, we could break them down in spectra. We understood the Earth a bit better. We could use the photoelectric effect, thanks to Einstein, to better understand these discrete energy levels of different chemical bonds and atoms. And the universe was looking pretty whole. So we now, again, thanks to Einstein, we understood a lot more about it, and we thought we lived in a universe. That was good. But there was so much more that was hidden. So we thought we lived in this, an empty universe. Maybe things were gravitationally, well, we know gravity obviously existed, but maybe we thought there was the old idea of it was pulling towards each other. This is before we understood what space-time was. So we thought the Earth just existed in the universe, not quite sure what the universe was yet, but we had a better understanding when Einstein published general relativity. Because now, not only were we just living in something, we were pretty sure it was not an ether, but we didn't exactly know what it is. We didn't know why gravitation was so inherent in everything that we saw until general relativity was able to describe space and time to us. Now, Einstein's field equations, what came out of general relativity, are a set of equations that you can use to try solve your universe, given a set of principles, given that space and time was connected and that it was bending. What was interesting, though, when Einstein first came up with the concept was this idea of this was still our universe. The night sky that you saw, that was the universe. I've put it in a little container there because we thought it was, well, Einstein thought it was a static universe, which made sense back in the day before we could really understand that galaxies were absolutely everywhere and incredible distances apart. The universe seemed pretty static. We knew we were moving around the sun, and probably the sun was moving around whatever this thing was that we lived in, the galaxy. But we weren't exactly sure that our galaxy was moving. That seems a bit far-fetched. Everything else is moving. This has to maybe stay static. And maybe the universe had bounds, which we are now not certain of at all. But when Einstein first solved these equations, he solved it for this type of universe, a static, closed universe. And it wasn't until the work of Hubble that really discovered that these nebula that we were seeing, these spots of gas that looked a little bit different to all of the groupings of stars, they were in fact galaxies. Other galaxies, bigger, if not, massively more larger than our own Milky Way, and they were on the move. We could now use the spectra that we understood very well to figure out that these things were moving both away and towards us, depending on where we're looking and what galaxies we're looking at. Which is just amazing, because all of a sudden our universe goes from being in this container to it could be boundless. The galaxies that we're finding, there's so many of them. And again, this was only our very local universe that they were seeing, but still hundreds and then thousands of galaxies that we could map that were moving towards or away from each other. And the general trend was that they were moving away from each other unless something was very close to us. And so we thought the universe is now not bounded. It is on the move. It is maybe expanding. And you could solve Einstein's equations for an expanding universe. And I think this revolutionized the way that we were thinking, because now we understood that we really needed to try and constrain space and time better, because it is on the move. Something is happening. It's not static. But what does that actually mean? So before we go any further, I just want to sum up that in the Roaring 20s, these people look like they're having an excellent time. And this is what they knew. They knew that there were different types of stars, that space-time was our fabric. We could explain gravity a bit better, that there were now multiple galaxies. It wasn't just the Milky Way. The galaxies were moving all over the shop, and that we could break down matter, light, in a relationship, so that that photoelectric effect, or E = mc squared, we could now use that to understand how matter and energy can go from one to the other. So great understanding of the universe as it was. And then we started to discover the dark universe. All of a sudden, everything that we saw wasn't necessarily it in the universe anymore. And it started with Vera Rubin. So we thought the universe was expanding. That can go on the side table for quite a few decades. We just accepted that we needed to understand that a bit better. It wasn't until Vera Rubin came along, and all of a sudden, it wasn't just this mystery of an expanding universe, it was a mystery of a heavier universe, because she was able to do something pretty amazing, again, using manual measurements of galaxies to figure out that they weren't rotating the way we would expect them to. So no matter what type of physics you were using, whether you were trying to use general relativity or old Keplerian physics, the outside of a galaxy should be rotating slower than it is. And it's just as simple how much mass there is, because on the outside of the galaxy, we can just visually see with our eyes there's a lot less stuff than the inside. And we can do some really clever light to mass ratios. So dependent on the type of light that we see, we can figure out pretty accurately what is the mass of that galaxy at given sections. And when we do that, you would expect to see that grey line there. So it kind of spins a bit faster where we've got a heavier outside of the ring, and it fades off as we get away from the galaxy. And that was not the case. What Vera found was that just from starlight alone, doing this light to mass ratio, it looked like the galaxy was plateauing. So it looked like it got to a speed and it just kind of stayed there, even when you were moving away from the galaxy. And that's that yellow light there, spinning a lot faster than we thought. We then could break it down even further and use radio observations of the 21 centimeter line to figure out that this diffuse gas in the very outskirts of the galaxy was also moving extremely quickly. There had to be something there that was weighing it down, making it heavier. There had to be, because otherwise our physics did not work. And this was a big realization, because all of a sudden, back at the beginning of the talk, we think we understand atoms, we understand light, we understand energy. None of that was interacting with what apparently was here. And this is still the case. So we called this dark matter because we knew it was heavy, it was having some type of effect on gravity, but it wasn't the type of matter that we interacted with every day. It wasn't what we call baryonic matter, which is what me and you and the stars are made out of. It was something different. And the further we looked in the universe, the more sky that we covered, we saw even more evidence of this dark matter. So this is just a stunning lens. And what is happening here is that galaxy that's in the center, that yellow galaxy, has so much dark matter in and around it, what we call a dark matter halo, that it is bending the light from a galaxy that is many, many trillions to billions, trillions is bigger than billions, trillions and trillions of kilometers away from it, in a different part of space and time, bending that light around it, which would only be possible if it was heavy. And sure, in theory, we could have a galaxy that was heavy enough just from baryonic matter. But when you do cheeky conversions there to figure out how much mass based on how much light we see, it is not enough mass, not even near close. And so dark matter was just becoming more and more convincing. So we're back to our universe now. Now we think it's even darker and there's even more that we don't understand. And all of a sudden, none of these things, none of this tries to explain what we're seeing or what we're not seeing really in dark matter. It does not interact with baryons. It's not atoms that we know it. Otherwise, we would think we could detect it here on Earth. And it doesn't look like it's interacting with electromagnetic waves. So we're not seeing that photoelectric effect. It's really bizarre. And that's kind of where we leave it, because we don't know what dark matter is. We still don't know what it is. We have some very good estimates, which I'll chat on a little bit later on. But at the time, it is still completely dark. We can't explain it. We can model it and try to predict what we think it is, but it is still a massive mystery. 100 years ago, they had no idea. 100 years further, we might still have no idea. But that's one to watch to see if we ever figure it out. The next thing that we come back to, so we now know that there's dark matter. We're coming back to what Hubble found, that this universe was expanding. And it was the work of Stephen Hawking and his colleagues to really try break down, okay, so if we're expanding, we must have come from somewhere very small. And this is the idea of that Big Bang theory. This was born, and we didn't know exactly what caused the Big Bang or what happened for a certain period of time after, but we thought we could predict pretty well on from a couple seconds afterwards what was happening. And from this, our predictions, if we assume a Big Bang beginning of our universe, meant that there was a rapid inflation. All of a sudden, space and time just rapidly inflated, quicker than you could even blink at, literally. And then just kept moving. And so there was a couple possibilities here. Depending on if whatever we think that movement force was, there's a couple things that could have happened. So we knew the universe was expanding, but we didn't know what type of expansion was happening. So it was possible that it could have decelerated. So if we came from a Big Bang, you can think of it like an elastic band. If you stretch it out, it wants to come back in. For a moment there, serious concerns that could be our universe. And if that's the case, then surely we come from a Big Bang, we must end with a Big Bang. Not a great outcome, and I'm very glad that that's not what we found. We also have the idea of a decelerating universe. So it's not going to come back on itself, but it is going to slow down over time. And then you have the coasting universe. So it is just like linearly progressing with speed. However, there was one model which was the accelerating universe, and this meant that through time, the further in time you got, the faster space and time was moving. And this is concerning. Well, not concerning, but we didn't know what was going to happen because we're still not sure if space and time is finite or infinite. It could either be one or the other. Who's to say? And if it is finite, if it is some type of limit, if we start accelerating too fast, what happens to space and time? This is where we get into the idea of maybe a big rip happening. But to confirm that, we had to do some pretty cool science. and it was using beautiful dying stars. So I'm sure you're all very familiar with when big stars die, we get supernovae. There's a heap of different type of supernovae. There's one very special type called a type 1a supernovae. This happens when we have a white dwarf and we think either another white dwarf, so very compact small stars, or a white dwarf that's basically stealing material off a bigger star. The models, we're not sure exactly if both could happen or if it's one or the other, but we know that consistently they explode with basically the exact same energy every single time. And we can do some corrections for the different colors that we see. But basically, they are a standard candle or a ruler. There's something that we know is very specific. And with that, we can use that standard candle idea of us actually using them to measure further and further back in time. Now, this is incredibly difficult because you need to have data from very far back in time. And there were a couple of things that could happen here. We could either see that we were one of those 4 different universe models. We were either decelerating, coasting, or accelerating. But we needed to see back pretty decent. We needed to see to about half the age of the universe to get any type of really good estimates. And that required us designing and using some of the best cameras in the world to try to capture light that is so remarkably faint. It's almost unfathomable to think that we are able to capture light that has traveled tens of billions of years to get here. But we did. And it was the HI-Z and the Wigglesy cosmology projects in the 90s that both independently confirmed this. And what we found from this data is that galaxies further away from us were moving slower. So if we go from us to our nearby galaxies, we're moving pretty quick. Say we've got a number, you could say that we're moving at 10. It doesn't need to have a scale, but we're moving at 10. You then go from that galaxy to another one further back in time. That's only moving at 8. And you keep going back and back, and you find that we are getting quicker, and it looks like it's not a linear progression. It is accelerating. And that is incredibly interesting because it's not quite what we thought maybe was going to happen, but now it allows us to kind of probe it a bit better to understand what is the physics behind this. So these are our modern day astronomers. So Saul Perlmutter, Adam Rees, and of course Brian Schmidt, who won the Nobel Prize for discovering this accelerating universe. And this was only in 1997 the paper was published, both of them, and then the prize was awarded in 2011. So in the last 20 or so years, that we have discovered that our universe is accelerating, which changes the way we think about our universe. So now we can kind of make an equation of what we think our universe is. We think we have pure energy, so this could be pure radiation. We don't have a lot of that left at the universe at the moment. We have matter, me, you, the stars, the galaxies. We have dark matter, that invisible thing that is holding galaxies together. And really, we think that dark matter, I forgot to mention this before, without dark matter having formed what we call the cosmic web, where we get big halos around galaxies and filaments in between them, galaxies might not have formed. There might not have been enough gravitation for all of the normal matter to have formed in the time frame that it is. So we might not be here if it wasn't for dark matter. And finally, we have dark energy, which is really governing what our universe is going to look like, because now we have this picture where we can try and predict the end of the universe, which, don't worry, not going to happen for a very, very long time, but it's fascinating because our space and time is changing quite rapidly. So the best way to try to describe it, I think, is if we just say we take a squared meter of the universe, of space and time. We can now put all of that into it and describe it, and this is the field that we call cosmology. So this cosmology, so we could confirm it using both supernovae, dark matter, estimates from around galaxies and around lensing, but we could also independently confirm that the cosmology we think is making up the universe, so about 30-ish% matter between normal and dark, 70% energy coming from dark energy, we could confirm that that was happening at the very beginning of the universe too. So So everything we've measured is what we call late universe, even though at redshift 1, that really is quite some time ago, but it is quite a long way through the universe's age. What we can see with the cosmic microwave background radiation, so that very first light that was decoupled from atoms when the universe went from opaque to all of a sudden visible, we can then measure cosmology and figure out different properties of this heat map. So this basically is a heat map of the universe at the very beginning of light time. So about 380,000 years after the Big Bang, this light was emitted. And what we can do is basically count up the little blobs, and we do this using a power spectrum. And depending on what our power spectrum is and what those moments are that we get, deciphers what the cosmology is. And it turns out, even if you ignored supernovae, ignored the lensing that you see, ignored Vera Rubin's estimates, the cosmology that we see of roughly 70% dark energy, 30% combined matter, and a bit of radiation, that matches this perfectly. So this was an independent confirmation that cosmology really, really was there throughout all of the history of our universe. And this is it breaking down a little bit further. So as I said, almost 70%, and this is what we call energy density. So it's how much density in whatever given square of the universe. So about 70% is dark energy, 30% between both matter and dark matter. And if you break it down even further, we are the tiniest little slither there of the stars, the galaxies, the dust, and us. It is insane that everything that you see and experience and wonder of the universe is the tiniest little slither of what is actually in the universe. And I thought I'd show this plot. It looks a little scary, but I think this is the best representation of what is actually happening over time with our universe. So to break it down, we've got 3 lines. We've got a radiation density, so how much radiation is there? We've got matter, and that combines both dark and normal matter. And then we have our green line, which is dark energy. So I think what is very easy to misunderstand when you hear of dark energy and accelerating, you think that there's more dark energy being generated, possibly. It kind of makes sense when you think we're accelerating faster, there must be more dark energy. Well, the dark energy is remaining constant. From all of our estimates, it looks like it is completely constant throughout time, which is pretty cool, because that means that the only reason the universe is accelerating is because we're getting less matter and less radiation, and we've crossed into a dark energy dominated universe. So all of a sudden, when that green line is peaking above both the others, that's when the acceleration is happening and what we're in right now. Whereas at the very beginning of the universe, a second or so after the Big Bang, completely radiation dominated. So our universe is just changing. She's growing up and she's blossoming and blooming, and it's awesome, because now we can take our square meter of the universe and we can break down what's in there. So say we take all of the radiation, the matter, the dark matter, and we have a clump of it. That is our thing that is acting on space and time. So we get a nice curvature because of space and time. We get gravity holding it together. But in our box, we have a constant force of dark energy, that constant line. It doesn't change, it's just constant all the time. However, it pushes a little bit, and as everything is evolving, our matter is evolving, and we stretch it just a little bit, you can imagine that some of that dark matter and normal matter all of a sudden has been stretched outside of that box. So we have less of it inside of our square meter. So we have less gravity acting on it. And then now dark energy, still the same, but it's easier. It can push easier on that box, and it just continues and continues until, well, we don't know how the universe will end, but we think it's going to get to a point where there is basically no matter, no radiation left in regards to our boxes, and it will be completely dark energy dominated and could even possibly exceed the speed of light with its acceleration. Now, that is a big prediction, and that, if it were to happen, would not happen for, I forget what the actual timeline is, but it is something remarkably silly. It is like 10 times more the amount of atoms in our universe, that to the power of 10 in years, an insane amount of time. So it's nothing to worry about, but it is fascinating because when that happens, then all of a sudden physics has changed, because we thought the speed limit of the universe was the speed of light. If this happens, then that speed limit is no longer the limit, which again, who knows what that will do for our universe. We won't be around to see it, but I like to ponder. So that is the state of our universe today. We now have more evidence of this universe we live in. We can now see that there is an uncountable amount of galaxies out there. We think, just based on our estimate, that there's 2 trillion, at least in our observable universe. Now, again, going back to if our universe is static or not, we don't think it's static. We don't think it's closed, which means that our universe very well could be completely infinite. And if that's the case, there's an infinite amount of galaxies, infinite amount of stars, and then possibly an infinite amount of life out there. But who's to say? So I'll quickly touch on the last 2. Now that we've had our minds meshed a little bit by how much we know and don't know about what our universe is, maybe we can ponder on if the Earth is special. So up until about 25 years ago, if we said, is the Earth special, we would probably say yes, because we hadn't detected exoplanets. We thought they might exist, but we hadn't seen anything else like it in our solar system. None. These were all the planets that we knew until 1992. Our 8 planets, RIP Pluto, that's it. That was all the planets. However, we did some pretty tricky things. We wanted to know if there are other planets out there, could they orbit all of the other types of stars? Because at the moment, we only knew that planets orbited sun-like stars. And this would have consequences. If you have a planet orbiting a bigger star, for it to be like Earth, it has to be further out. And we don't know if planets could form like that. So the best way to try to detect them was using something called the transit method. So using dips of light when a planet passes in front of a star to try then do some math to figure out how big is it, how far away is it, and what is its orbit. And using this method just in the last 20 years, from both, we've had Kepler, very successful, and now TESS, who's doing all of the hard yak for us up there. We've found over 5,000 confirmed exoplanets just in the last 20 or so years. So we went from knowing that there was no other planets out there to all of a sudden there's 5,000. And we think if we extrapolate back what we've looked at, that there is an insane amount of planets in our galaxy, tens and tens of billions of planets. And most of them, we think, are probably not habitable, at least for our life forms, not habitable because they're too big, they're too gassy, they're too hot. But we do have some Earth-like planets, some super Earths that we've found that we think possibly could harbour life just like us. So that brings us to our final question. Are we alone? And I always answer this with how could we be, with this as being our universe? Again, this tiny little Hubble deep field is that tiny, tiny little box there. Every point of light bar 2 in that image is a galaxy. 2 stars, all galaxies, which is insane. And most of those galaxies are bigger than our Milky Way. And again, we're looking back in time, so they're probably even bigger now. How could there not be life out there where we have an uncountable amount of stars and planets in our very own galaxy, and now we are just multiplying that by the rest of the universe? So I'll leave it there. If you want to chat to me about how life could actually form on other universes, or other universes, not multiverse, we're not here for that tonight, other planets, please come and chat to me. But I will finish off with James Webb might help us, because we might be able to look at some of the spectra from the planets to try to figure out, does it have water, does it have oxygen, all of that good stuff. And of course, we might be able to listen. But with that, I welcome any questions, and I hope that we had a good adventure through the universe. Thank you very much.
Well, why don't you clap like that for me? Oh, I got boos. Now, if anybody has a question for Sarah, pop your hand up, and through the blinding light, I'll see if I can find you. What I can say is the only people who know about multiverses is Kevin Feige. He's the man to ask. We have a couple of questions. I'll come over here first. Oh, he's checking his notes.
Hi, Sarah.
Hi.
Sorry, a bit loud. There was multiple big bangs before ours, and ours developed from a series of bangs that cycle throughout time. If this is the case, where do you think the first bang started, and do you believe this could be connected in any way to a theory of everything, if true?
I like that. So I've heard that theory before, that there were multiple bangs. I don't know if that's the case for our universe as it is, only because we're accelerating. Unless we've broken the cycle, maybe there were bangs, contracted bangs. We would never know. We could never, ever, ever know. But it's not an unreasonable theory, because we don't exactly know what caused the Big Bang. And it was a silly amount of energy that just happened at the time. So I don't know the answer to that, but I love that theory. There's also a theory, multiverses, where infinite amount of bangs happened at the same time, an infinite amount of universes. And just statistically, every type of universe you could think of happened. All of our constants, the speed of light, alpha, everything we consider a constant is different in every universe. But with each of those theories, the saddest part is we would never know, but it is nice to ponder.
Do we have any other questions from the crowd? Oh, Brenton's got one. Of course he does.
It's about dark matter, and they say that as the universe gets bigger, that dark matter is a function of the space between everything. I heard Dr. Watson say that, one of your things. So if that's the case, then was it not then that when the universe, when it started, the Big Bang, was dark matter always there? And so now the property of it as it's expanding, is it because the universe is getting bigger, or is it because of the property of the dark matter itself that's making which is it?
So if we think dark matter is a type of matter similar to what we see, obviously not the same as us, but assuming that it is broken down into atoms and maybe some subatomic particles, then we think that it probably formed the same time normal matter did, because it would have, so all of our matter has formed through an interaction of a heap of different quantum mechanics fields, just sheer probability that we have matter. And we had just slightly a little bit more matter than we did antimatter, and that's why we're here. And the same thing must have happened with dark matter, or at least we think, if it's a particle. But instead of the same ratio between matter and antimatter that we had to get us, it was a lot more dark matter to a lot more, if there is dark antimatter. But we think it all may be formed at the same time in those couple of seconds to minutes after the Big Bang, but we have no idea. The etheric.
We're just having a general conversation between you two, are we? Yeah? Do we have any other questions from the crowd? No. I think you've stunned them with knowledge. Well, Sarah, thank you very much for joining us tonight and sharing your 100 years of history with us. And I do love the Contact, the end one. Great movie. Now, before we jump on to the next speaker, Lee, or actually no, Claire, that's your name. Claire's going to come and set up. But while she sets up, I'm going to have a chat to you guys at home and here about a wonderful major event that the ASV is about to launch to the public. The members will know about this event. Hang on, I've been told to walk back this way. Happy now? Yeah, he's happy. The members will know about this event, but the public won't. For some time now, we've been working behind the scenes on creating a major Astrofest festival up at Sea Lake and Lake Tyrrell. So for those who are not members of the ASV, and even for those who are members of the ASV and haven't yet checked it out, head to www.sealakeastro.asv.org.au. It runs from the 29th of October to the 31st of October, so starting on the Saturday, finishing on the Monday night for the long week, Melbourne Cup long weekend. There is science for the kids, solar observing, deep sky viewing, astrophotography sessions, silo art sessions, keynote speakers. Sarah's going to be one of those. Thank you, Sarah. Fred stood us up, but that's okay. We'll get him next year. All sorts of Q&A dinners, science in the pub. of that wasn't me for once. Science in the Pub quiz, you name it. A lot of events to support the Sea Lake community. It's in conjunction with Berkshire Council and the Sea Lake community. So go to the website and check it out. Are you ready? Done. All right.
Can I turn it on now?
You have to turn it down. Technical difficulties. All right, wait a second. I've got to do my intro. Here with us tonight to talk about what's up in the skies for July is Claire Kenyon.
Okay. Now, Fred, you told me to come up here and razz everyone up. Did I do it okay? This is horrible. I hate speaking into these things. Okay, how's that? Good? All right, excellent. All right, just quick draw McGraw here. We should be able to see my screen. Are we going to switch it up? First of all, thank you so much for having me. I did actually do the same thing last month, so obviously you didn't get too tired of me, and here I am again. Either that or you just couldn't get anybody else, so thanks, Mark. Thank you so much. I'm a science communicator and astrophysicist. I'm actually in the process of moving to Adelaide to write for Cosmos, so this is a really good way to just make sure I stay in touch, and I'm sure Mark will have me down as much as possible. Yeah, of course you do. All right. Anyway, so I'm here to talk about what's up. Normally the title would be What's in the Sky, but because I felt really helpful for Mark today, I changed it to What's Up. It's just a little joke because he always calls it that and it's not that, but that's okay. All right, here we go. So just a quick handy tip, but I talked about this last time for observers. If you have your hand out in front of you in the sky and you have an average hand, not like my little tiny grade 5 hands, we got 1 degree of arc. Also, it doesn't help me because I can't do that, so I do it that way. Or 5. Or we've got 10, 15, and 25. Incidentally, I just learnt today, I was this years old, that that's about 90 degrees. That kind of freaks me out a little bit. And then there's this other one where, anyway, so there we go. So there's some good rules of thumb, some handy hints on how to find some degrees of arc in the sky. So when you look at the moon, of course, and you put your little finger up, which just looks really rude, doesn't it? Hey, moon. Yeah, I can see what you're doing there, Mark. Hey, moon, right? Does anybody know how much of your finger the moon should be at the distance of an arm away? 0.5. Yeah, 0.5 of a finger. It sounds weird as well. I might just move on from there. Anyway, so there we go. If I talk about any degrees or anything like that today, if I say I look at 10 degrees above the horizon, you'll have pretty good vision to be able to see that. But, 20, 30, 40, whatever. You'll look really kind of weird as well because you'll be sitting there doing this. All your astro pals be like, dude, what are you doing? All right, so I thought I'd start off talking about what you can see in the sky. So what's up? Of course, I love the ISS, and I thought I'd give you a little bit more information this time on the ISS. Just one time to see it this month that's really, really good, but you get a lot of time. You get 6 minutes, and it's all the way up at 88 degrees. Basically up there, all right? So that 88 degrees, it's going to, do not look too closely at this. It has been doctored in a way that, it's taken me 9 years to get even closer submitting my thesis. So this has been doctored more than I have. Anyway, so I've doctored this a little bit, so don't look at that. So here we go. So what happens is the ISS will appear above the southwest, rise quite high. In fact, the more astute of you will realize it actually can rise a bit higher than that, up to 88 degrees, and then disappear in the northeast. You get 6 minutes to look at it. Really good viewing. Why does anybody want to look at the ISS anyway? Who cares? Well, this is well, it's really cool, right? You can look at it. It's like actually quite clear. It's a beautiful bright dot. I can't see anybody, but please feel free to be interactive and raise your hands if you've ever actually gone out and looked at the ISS. Hey, look at that. Oh, look, I get to see you all. Fantastic. Okay, and also you get to know that, you're all part of something here. So speaking of being part of something, these guys up there in the ISS, Expedition 67, This is who they are. So we've got 3 cosmonauts. I'm not going to pronounce their names because I feel like I'll do a poor job. But we've got 3 cosmonauts, and then we've got 4 astronauts. What I really love here, just to relate to Sarah's talk, is that this looks a lot different to what we're looking at, you know, those women computers. Yeah. Put that in your pipe, right? So there we go. We've got Samantha Cristoforetti and Jessica Watkins really out there, being visible, well, up there, I suppose. So why do we care anyway? I mean, you're going to look at this dot and go, oh, yeah. What do you care? Why do you care? What are they doing? Well, while you're looking at the ISS and it's flying over your head almost at 90 degrees, know that they are growing plants up there in this wonderful program called X-Roots. So they're doing hydroponic. Of course, hydro, you know I love words, right? So hydro, of course, is water. Great. And we've got aeroponic. Can anybody guess what that is? Yeah, so aeroponic plants. So what they're doing is they're putting the seeds in and actually cultivating these plants. And the idea is that hopefully one day they'll be able to grow food up in space enough to actually feed whoever's on the station or whoever's in, well, probably not going to be the station, because let's be honest, it's not going to be up there for very long. But, you know, when we are actually in a place up in space and living there for longer, then we'll need to grow some food. But it's not just about those selfish astronauts making food for themselves. It actually is all technology that they're hoping to bring back down to Earth and help people grow crops on Earth where they don't have favourable soil. What else are they doing? And why else should you care? Well, here's Cristoforetti in this thing called a smart shirt for wireless Compose 2. It's not really got the same sort of ring to it as like Nike, but I'm sure they'll work on that. So what is this? Well, in this shirt, they actually have sensors for body temperature. They have sensors for your heart and your cardiovascular system. And of course, they need to have something where they can actually send it. I'm sure they'll have to work on that little wireless component because I'm not wearing that. Anyway, so this is really cool. So what they can do with this is they can actually look at the effects of space on the astronauts at any one time. I imagine eventually this will be used by, you know, Nike and Adidas, or however you like to say it, Adidas, to see how their athletes are going. So this is quite cutting edge technology in that area. So they're looking at how, you know, everything affects the cardiovascular system. And also potentially at some stage in the future, possibly control free flying robotic systems, because it can actually sense your movement, which is cool, really cool. And finally, of course, the ISS, we see these wonderful pictures where it's looking down. So what it's looking down at here, these particular photos, are 2 volcanoes on the Chile-Bolivia border. The top one is called Paranacotta, and the bottom one is called Pomerape. Now, they're both over 6.4 kilometres tall. They were active 100,000 years ago. And frankly, I just think that's absolutely stunning. And if that was the only reason the ISS was up there, I'd be okay with that. So I've just told you to go out and look at the sky, look at the ISS. But how about when it's really, you know, not great weather? Because, you know, let's face it, we live in Melbourne. How about you do some oral astronomy? So what am I talking about? Well, there's a Houston, we have a podcast. And the reason I actually put this up today is because they actually get people on the ISS on these podcasts. They have ex-astronauts. So this particular one, Houston, we have a problem. It's an official podcast of the Johnson Space Center. So you get astronauts and scientists and engineers on this podcast. You also get, if you have a look, there's Curious Universe. That's really good for people that are just starting out. Anybody that's curious and, you know, anything that's up there. So they're really easy, singular bites sort of podcast for you to have a look at. And they're just a random exploration of space topics. What else can you do? Well, you can listen to On a Mission. Now, On a Mission is stories of scientists that have been on missions, not necessarily scientists on the mission, but they've been working on missions that actually go out into outer space, which is absolutely incredible. You might want to have a look at Giant Leaps, Small Steps and Giant Leaps. I'm sure it's supposed to be in that order, which is the moon missions and then beyond. So looking at future missions to other places. And finally, you might want to look at the Invisible Network, which is actually about all the stuff behind the scenes. Did you just see something else pop up in the corner? Oh, yeah, I don't know. What is it, Fred?
Never heard of it.
Oh, never heard of it. Okay, don't worry, nobody else has either. No, I'm just kidding. do actually love Fred dearly. This is Space Nuts, which is a podcast by our own dear Fred Watson and Andrew Dunkley, I think. Yeah, so absolutely fantastic. You can listen to Fred's dulcet tones, beautiful northern tones, Northern England tones into that microphone whenever. How is it, weekly, monthly?
It's weekly, which is why
Weekly.
I don't have any hair left anymore.
So yeah, you can have a listen to that. And I would be remiss of me, Mark, to miss a certain other podcast that we know something about. You don't spruik it to anybody, do you? So Spaghettification, of course, Mark and Steffi Bernard. I have recently just taken a little bit of a hiatus from there, but I'm sure you'll hear me back again. So if you're bored and you can't see anything out in the sky, or even if you can and you want to hear those different things going up there, ISS astronauts and all that, and Mark, pop on your headphones and have a look on Google Podcasts or Apple or wherever else they are. Anyway, so I thought I'd tell you about the moon because that's there. So 7th of July, which is not tomorrow night, the next night, we're looking at first quarter. Beautiful time to look at the moon. Wonderful time. Less great, waxing gibbous. Even worse, full moon. So the full moon has a little cape. Okay, that's because it is a super moon. Does anybody know what a super moon is? I know that was my own little joke. Did you like that? Yeah, I was pretty proud of that. That took me all of 10 seconds. So this full moon this month in North America is called the buck moon. Buck as in like deer, right? I don't think that's all that appropriate here because most of the deer, all of the deer that we have here, well, no, some of them are in pens, but the rest of them we don't really want to be here. They're not native and we don't really want them, and it's not appropriate to call the moon after them. So, super moon, I thought I'd tell you about that instead. I just told you an irrelevant story. Another largely irrelevant thing is a supermoon. It means very little. So what do I mean by that? Well, a supermoon literally means that the moon is so the moon's path is elliptical, right? It's not actually a nice circle around the Earth. It's elliptical. And you might all, of course, remember that wonderful number, 384,000 kilometres is the distance from the Earth to the moon. Yeah, not very often, actually. So it varies between 356,500 kilometres to 406,700 kilometres. So it sort of does a little bit of an ellipse. Nothing's really a perfect circle in the universe, let's be honest. So when the moon is close to the Earth, we call it perigee, near the Earth. When it's far away, we call it apogee, because that's away. So when the moon's closer to the Earth just a little bit, it's at perigee. And when it's a full moon, that's a supermoon. Pretty easy. I challenge you to notice the difference in the sky. And you're going to get out there and you're going to be like this. No difference. And that's why I call it largely irrelevant. So we've got a waning gibbous moon. It's going to start to go towards full moon. We've got July 21st will be the last quarter. And we head on into waning crescent and the new moon on the 29th of July. Now, just like last month where I gave you a couple of moon targets, I thought I'd give you another couple this time. So as it's waxing into full moon, I thought, why don't you go and seek out this little site here? This is the landing site of Apollo 17, which actually was the last Apollo mission to visit the moon. And it landed in this place called the Taurus Latrobe Valley, which is actually deeper than the Earth's Grand Canyon. And what's really cool about this, on 1972 in December, which is when it landed, it actually was the first professional geologist on the moon. There you go. There's some trivia for you. You know, you'll be sitting in the pub and somebody will be like, now, when did the first professional geologist land on the moon? And you'll be like, 1972, it was December. And I'll be proud of you. So they brought back samples that were beads of volcanic glass from an ancient lunar fire mountain. So how do you find it? Find the little bum, butt crack, okay, and head down. Find the coccyx. So on the waning moon, so as the moon passes full moon and goes towards new moon, I'm going to challenge you to find, does anybody know where that is? Who told? Did you see my slides? Okay, you're right, it is on the moon. I feel like that was low-hanging fruit, but you got it. You got it. Fruit is good for you. So this is Schiller crater. Now, Schiller crater is up here. Why is that even interesting? Well, here's the thing, right? Near the moon's edge, all craters actually kind of look oval. This is because of something called foreshortening, right, near the limb. Now, Schiller actually is oval. It's actually elongated. So it's 180 by 70 kilometers, and it was actually probably formed by the impact of an asteroid coming in really flat. You just had a visual, didn't you? It was like, oh, no, I did. I get distracted, sorry. Anyway, so that's the other moon target that you can have a look at. And you can know that most of the craters around there actually are circular, but that one there, this kind of weird little slug thing, that one's not. Another piece of trivia for those bar nuts.
Something interesting.
Oh,
There is actually a geologist on the moon right now.
really?
Yeah, and that geologist is going to talk to these
Really? On the moon?
James Shoemaker.
I didn't think we had anybody on the moon yet.
James been up there for years.
Oh, the ashes. That's amazing. I didn't even think of that. And actually, I think Shoemaker was one of the sort of first people to really get planetary science going, wasn't he? He was one of the sort of fathers of planetary science, which is amazing, incredible science. As an ex-geologist and sort of current talker of astrophysics, I really, really like planetary science. Okay, so the sky, when you wake up in the morning, of course you're going to get up at 1:46 to see Mars. And when you're up to see Mars, you'll notice that Jupiter got up before you. Lazy. So Saturn is going to be out there tonight. So wait till midnight, you'll see Jupiter. Before that, you'll see Neptune if you've got a scope. And we've got all these out there. Now, at the end of the month, not much changes. Mercury's still in bed. Mercury's still visiting the sun, and I'm actually going to talk about Mercury in a little bit. But as you can see, obviously, the sun is starting to eat into the dawn. Mark said I could heckle. Okay, so I thought I'd just run you through a few conjunctions and pulses just to remind you. Conjunction is when the right ascension, which is one of the two coordinates that we use to find things in the sky, most of you astronomers are like, yeah, hurry up, when they're the same for two objects. Now, in a pulse, of course, a lentil, a pulse, a beam, it's when things are together, close together in the sky, so they're visually close. Okay, they don't necessarily share the same right ascension or coordinate, but they're close. And sometimes pulses happen and they'll look like they're right on top of each other, but they're not sharing the same right ascension, so they're actually not a conjunction. So anyway, what do we got? Well, the soonest one will be Saturn and the moon. So the moon is doing this thing this year where it's just visiting them all. It's like, hi. So it gets in with Saturn. It gets in with Saturn and says, hi, Saturn, how you doing? And then it says, I don't really like you. So look 2/3 of the way up from the north horizon, so 66 degrees. It'll be highest point in the sky at about 2:30 in the morning. Of course, you're all going to be up at that time doing that, aren't you? It's going to be about 4 degrees apart. That's right. It's never going to get old. So I said I was going to talk about Mercury. Now, Mercury is at superior solar conjunction. And you know I love words. So, of course, this is the best one, right? So superior solar conjunction. Well, yes, okay, so it's going to be in a conjunction with the sun. Does anybody know what superior means in this context? What's that? Oh, I don't think you want to see this. That's what the monkey's telling you. Don't look. So superior conjunction occurs when a body, like a planet or an asteroid, it could be a comet, lies along a straight line joining the Earth and the sun, but it's on the opposite side of the sun from the Earth. So that's superior solar conjunction. So please do not try to look at that. I just thought I'd tell you that that is occurring and that you can't go and look at it, because I'm that sort of person and I get joy in telling you can't do things. I feel like my mum. This will happen every 116 days, and it marks the end of Mercury as a morning sky object, and from now on we'll start to see it in the early evening. Oh, you know what? Random clicker. Here we go. So we've got next. I told you the moon was philandering. It's gone to visit Jupiter now. And it will be there early in the morning. Look up from the north horizon, about halfway up. I'm very liberal with that. I'm hoping you can find the moon, and then you'll be able to find Jupiter. This time, the moon's getting a little bit more excited. It gets 2 degrees. It's not 4 degrees anymore, it's 2 degrees to Jupiter. After that, we're going to have a conjunction with Mars. Now, the moon actually likes Mars best of all. It's only going to be 1 degree away. Okay, so if you're looking at a red dot, you go, I'm not really sure if that's Mars. If the moon is right next to it, it's probably Mars. All right, and that'll happen on the 22nd of July. Now, there are a couple of other things happening as well. Uranus will also have a conjunction and a pulse, which is what that A means. So it's going to be close by to both the moon and Mars. But you probably won't see it unless you've got a scope. Now, here are some more things that you won't see. So Mars is going to have it's going to be a lunar occultation of Mars, and then there's going to be a lunar occultation of Uranus. And unless, actually, I don't know that for sure. I don't know if is anybody traveling to these places on these dates? Okay, then I can say this. You're not going to see it. Okay, but it's happening. So you might see some fun pictures. So what that just basically means is there's Mars, the moon's like, goes in front. A bit like an eclipse. Essentially is an eclipse. So that's that one. Boo, we won't see it. And finally, on the 27th of July, when the moon is just the smallest sliver, you'll see, what planet's that? Nope. It's Venus. It's Venus. But you probably, again, I should have had the monkey again, it's going to be at 10 degrees. That's right before the sun. So just be really careful. All right, Jupiter is going to end retrograde, is going to go into retrograde motion on the 29th of July. Handy little GIF. I love that. So retrograde motion, of course, is every night if you take a picture of Jupiter in the sky at the same time, you'll notice that it actually goes a certain direction through the constellation. When it goes into retrograde motion, it starts to move west through the constellations rather than its normal eastwards direction. So if you really like getting out there and taking a photo and carefully plotting positions, this might be a good activity for you. Aha, here's another thing that you can do that isn't looking at the sky necessarily, but it is. It totally is. Has anybody heard of Project Zooniverse? You might have heard of it in the context of like categorizing galaxies. Yeah, look what sort of shape they were and sort of telling researchers what you were looking at. And that's because we have so much data, we just can't get through it all as astronomers. So we actually use the public's help. Now, this is cool. This has the coolest name. It is exactly what it sounds like. Jovian, Jupiter, Vortex, Vortice, Whirlpools, Hunter. You're looking for basically air, cyclone shapes on Jupiter. So this is what you'll do. You'll go into the site and you just sign up. It's completely free and you get to look at. It's pretty rubbish though. You probably don't want to do this because these pictures are horrible. They're just awful. So what you do is you'll get in there and you'll actually look at beautiful pictures of real pictures of the atmosphere of Jupiter, and you can go there and you go, okay, the color, it's going this way, it's this type of cyclone. Is it a brown, forget what it's called, it's like these brown sort of disky things that are long, and then you talk about the color and its actual direction. And what you're doing is literally helping scientists understand physics of Jupiter, which is absolutely incredible that we can all be involved in that sort of thing. So those of you that want to get out the scope, I have some really big challenges for you. Here we go, 134340 Pluto. You may have heard of Pluto. On the 20th of July is at opposition. What does it mean? It doesn't mean it's sitting there ready to go. It means it's on the opposite side of Earth to the sun. So it's typically the best time to have a look at these really difficult to see objects like asteroids and planets. If you do want to look at Pluto, you're going to want a CCD. You're probably going to want a big scope, I'm thinking 12 inches, and you're going to want some clear viewing over several nights if you want anything more than a tiny blob. Next, we've got meters. 9 meters is opposition. Now, just be careful, this is not the moon of Jupiter. For some reason, they decided to name about 4 of the moons of the Jupiter the same as the asteroids. Very, very helpful, thank you. Just look for the number in front. That means it's a minor planet, not a moon of Jupiter. So this is at opposition, again, on the other side of Earth to the Sun. You can have a look at that. Now, this is about Mag 9, Mag 9.7, so you're going to want to scope. Also in Sagittarius is this final one, 192 Nausicaa, is at opposition. 9.6-ish, it's another main belt asteroid, diameter of about 86 kilometers. So if you're interested in this sort of thing, go for it. Now, Venus here is comprised of silicates and metallic nickel iron, but this one's actually an S-type asteroid, which is a little bit rarer, and it's made of stones like silica and silicon dioxide, which is basically what silica is. Okay, so while you've got your scope out, take a look at these comets. You're going to need a really good scope for this. So if you want to get to the dark sky site and open that up, go for it. We've got 3 comets here for you to look at. I love the name of this, it's just fun to say. 73P Schwarzmann-Wachmann. Yes, go have a go at that. Max Mag 11.1, good luck. And Helen Roman Alu, it's not the same. This doesn't feel the same. This will be in Sagittarius, worth having a good look at. And then Shoemaker Levy, not 9, 4. That will be in Taurus, and that's going to be about 11. So what's interesting about these? This is interesting. Does anybody know when that was? So in about 2017, when this comet came around, so it has a 5.4-year orbital period, this one, Schwarzmann-Wachmann, right? It started to disintegrate. And there were all these like rumors that a piece was broken off and coming towards Earth. And NASA was like, no, it's not going to. And guess what? It didn't. So, I'm going to trust them. So this one here has a period of 8.25 years and a mag of around 12. It's what's called a quasi-Hilda comet, right? Which is a Jupiter family comet that actually interacts strongly with Jupiter, and it has this sort of resonance with Jupiter's gravitational field. Now, about 8% of these comets end up smashing into Jupiter. So who knows, something for the future maybe. And this one here, Shoemaker Levy 4, has a period of about 6 years and a diameter of about 5 kilometers. Apart from that, it's about, Jupiter family comets typically have orbits of about under 20 years, and their orbits are primarily determined by the gravitational tugs of Jupiter. So put that away. You don't need the scope for this last bit. Wonder what these are. That's not to scale, and it's not accurate representation. Meteor showers. Good time of the month at the end, right? It's about the 29th and the 30th, perfect time to get out, lie back and have a look at the sky. And they're all in the same area, over in the east. So on the 29th of July, we've got the Pisces Ostrinids, probably my favorite one to pronounce. Not going to be the most amazing thing to look at, but fun to pronounce nonetheless. You've got your Alpha Capricornids on the 30th of July. Now, when I say they're on the 30th of July or the 29th, I mean that they peak then, right? They're going all the time. So they're actually going at the moment on the 3rd of July. They're going, right? But they'll be nicest at the end of the month. So they're not that great either for 4 meteors per hour. Now, the Alpha Capricornids actually have a parent body. So a comet, I was talking about that comet that broke up? Yeah, so what happens is this comet called 169P NEAT, right? And actually it's coming to reach perihelion, so it's reaching close to the sun on the 13th of July, so pretty soon. And it has a period of 4.22 years. So it comes in and it sheds off all this stuff, and then the Earth is like driving through the field of bugs, and it just goes, and then the Earth just goes around again. It just goes through the field and goes, okay? And there's actually another one over there as well, because the comet's gone round. Okay, so that's essentially what's happening. And yes, I'm on the record somewhere in broadsheet talking about driving through a field of bugs. So thank you, reporter. Anyway, so that one was a comet. And then this is going to be much nicer. This is worth getting the picnic blanket out for. So 23 meteors per hour. It's not that many, but who cares if you're lying back and having a look at the sky. Again, it's going to be really nice at the end of the month. And the Southern Delta Aquariids have their parent body in this comet called P2008Y12 SOHO, which was discovered by SOHO. And actually SOHO was a heliospheric observatory, which means it looks at the sun. And it actually was looking at a bunch of comets. And actually the ones that are periodic are quite rare. So they were quite excited when they found some periodic ones. Now this one actually has a period of 200 years, right? But its perihelion will be in early March 2025. So put that in your diaries. Tips for meteor showers, just quickly before we end up, rug up. It's cold. I mean, I get cold. You don't have to rug up if you like it, but I get cold, so I rug up. Take a hot drink. Now, what you put in that thermos is up to you. I told you, it's only 23 an hour, plus 4. I know what I'm putting in there. Blanket and a pillow. Now, it doesn't have to be a watermelon. Okay? But a lot of people make the mistake, they get a chair. Or they stand there. And they wonder why tomorrow they're like, yeah, you get to look up for a while, but you need to look down for a long time after that. So get yourself a watermelon aiming pillow and a blanket, lie back. If you've got those beautiful river chairs, they're good too. What else? And some air guard. I find that when I'm lying near the grass, this is the stuff you forget. And then the person next to you goes, why didn't you bring the air guard? This is horrible. I'm going home. And then you miss all the meteors, right? So here's your little packing list. Find a dark, comfortable site and give your eyes time to adjust. If you can, head out to the country. Now, the radiant, that is where it looks like the meteors are coming out of. And we say, Sagittarius, or we say the Leonids, because they come out of that. They look like they're coming out of, centering out of that constellation. Now, it's good to find the radiant, so it's a center. Better when that's high in the sky, when the radiant's high. Now, use it to find where to look, obviously, but then don't look there. Look about 30 to 40 degrees away. Okay. And the reason is that they look like they originate there, right? So you'll get these streaks coming out all over, and if you're just sitting there looking in the middle, you're going to miss all this stuff. And that's where all the good stuff is. So 30 to 40 degrees out, okay? If you want to take some photos, DSLR, wide angle lens, tripod, Lego optional. And you want a long exposure time if you want those beautiful streaks. Pull around with it. The end of the month's a great time to actually sit there for a couple of hours and just see if you can get something cool. There's your summary. If you want to, I know some people like to take a picture of the summary. And for some of you, I thought, you're sitting here going, oh yeah, we know all about these. Well, I'm just going to leave these here. And if you know what they are, go and observe them. Thank you.
Thank you.
Stay away from me.
I expect to see a lot of watermelons up at Deep Sky section.
You expected to see what?
A lot of watermelons at Deep Sky section. There's no watermelons underneath heads.
Can we bring a cantaloupe?
Oh,
Honeydew?
can if you want.
Oh,
Take a pick. But some of those dates are perfect because our next Deep Sky is the 30th of July.
easy.
So
You'll all bring a watermelon.
everybody come on up to Deep Sky. Paul won't mind. The more the merrier. Thank you very much, Claire.
Thank you.
It was wonderful. Now,
Brilliant.
while Claire fiddles around and removes her stuff and Fred comes up and does his stuff, I'm going to introduce him.
Why was that there?
We'll blame the last speaker. Give that one to Fred.
Yeah, Fred, it's
Fred can have
it's slightly less circular, more elliptical now.
Sorry, Lee. That
Thank
wasn't
you very
Sorry,
much.
Lee. Please
You
don't
can't
make-
get good help these days.
No, I know.
Okay, now, Mr. Watson, Professor Fred Watson, AM, has been the Australian government's astronomer at large since 2018. He worked at both of Britain's royal observatories before joining the Australian Astronomical Observatory. I'm doing the right thing. As astronomer in charge in 1995, and he's best known today for his award-winning radio and TV broadcasts, books, music, dark sky visiting, and co-hosting the popular Space Nuts podcast that Claire mentioned. It's way better than mine. Fred has an asteroid named after him. Oh, ours. Has an asteroid named after him, 5691 Fred Watson. But says that if it hits the Earth, it won't be his fault. I'm sorry, but it will be. It's totally going to be your fault. His latest book is Space Warp, Colliding Comets and Other Cosmic Catastrophes, aimed at a 10-plus age group. And tonight he's going to talk to us about Elon Musk. Well, a little bit about Elon Musk, I'm sure. We'll blame him. And Skynet, as I like to call it. Astronomy in an era of satellite megaconstellations. Most astronomers know that we are on the brink of an era of satellite megaconstellations with up to 100,000. Do you want to read it out, or do you want me to?
No, I'm going to talk about it.
All right.
It's a waste of time.
All right, I won't read that anymore. Without any further ado, Fred, it's all yours.
Thank you, Mark. Thank you, everybody. Thanks very much. Let me get rid of the color chart because I want to add to other people's acknowledgements of country, my own, of course, to all our traditional lands, but particularly to the Guringai Nation of Northern Sydney, partly because that's where I live and work, but also because it's where you can see that real emu in the sky. The beautiful picture that you've just seen was painted by Carl Piquet. That's the real thing, but not very far from where I live, there is also the real thing in rock art. It is on the Elvina track near West Head. Sadly, it's not really easy to get to. Perhaps that's a good thing because we don't want people desecrating it. But that is the real emu in the sky. This picture courtesy of Ray and Barnaby Norris. So, well, look at this. We're celebrating happy 100th birthday to the Astronomical Society of Victoria. And well done for making it this far. I remember most of those 100 years, not quite all of them, but it's always been a pleasure and a privilege down to Melbourne and talk to the Society, and more especially talk with the Society because you're doing some fantastic things. Now, we don't have very long to go, and it's absolutely freezing. I don't know whether you're feeling as cold as I have been. I'll pass my scarf around if anybody really needs it. So I will make this as quickly as I can, but I want to talk about something that I think we're all familiar with, and most of what I'm going to say is known to you, but perhaps you haven't heard it all together in one place as I'm going to describe it now. I want to talk about our new era, which we're on the brink of in terms of satellite mega constellations. That's me and the universities that seem to put up with me. My job is the nation's astronomer at large, which is a great privilege. I work for the Australian government in the Department of Industry, Science and Resources, which consists of 2,400 grown-ups and one astronomer, and it works very well. Occasionally, though, they give me grown-up things to do, and actually this talk came about because I had the, privilege, I guess, earlier in the year of addressing not quite the United Nations, but one of the United Nations committees about this topic, and that this talk grew out of that. So it's a little bit wordy, but it does describe what's going on. So it's like all the best talks, this is a trilogy in 5 parts. I want to talk a bit about how we protect the night sky. This is probably fairly familiar to many of you. I want to talk about the daytime sky as well. And then the new kid on the block, which of course are those mega constellations. Is this the end of astronomy? No, of course it's not. In fact, it means that we might have new opportunities. And so I hope by the end of this talk, you will be feeling maybe a bit happier than you might be at the beginning. It's always a risky topic, is satellite mega constellations. But let me start on the Earth before we go into space, because we're all familiar with this phenomenon of light pollution from terrestrial sources, mostly big cities. And it's, of course, very, very damaging to our view of the sky, which is why you've got this wonderful dark sky site out there in the country. However, that notwithstanding, Australia is actually pretty dark, given the size of our continent, especially when you compare it with some of the places to the north of us. This is a light pollution map, easily downloadable from the World Wide Web. Our place is dark because most of us live around the edge. And even in the cities around the edge, it's possible, if you've got the right kind of equipment, to photograph the Milky Way. This is a picture taken from not very far from where I live. I didn't take it. It was a David Malin Award winner a couple of years ago by Tom Elliott. It's the Barrenjoey Lighthouse, which is right at the northern tip of the Metropolitan District of Sydney, but there's been no photoshopping there. That's a genuine image of the Milky Way above the lighthouse, a beautiful one too. So given that light pollution is, well, it's a pandemic in the sense that it is everywhere, certainly as far as cities are concerned, and in the country as well, we need to think about how we protect our observatories. And the National Optical Observatory is at Siding Spring, one of the peaks in the Warrumbungle mountain range, Warrumbungle being a Gamilarey word meaning crooked mountains. There they are in the background. That is the dome of the Anglo-Australian Telescope. I always used to tell people that I've worked in that building for so many years, I started to look like it, but it's kind of worn a bit thin because I definitely am starting to look like it. So that needs protection. The biggest telescope, biggest optical telescope in the country is inside that dome, the 3.9 meter Anglo-Australian telescope. It is still doing world-class science. I'm not just bragging about that because I was its astronomer in charge for 20 years. It's now under the absolutely capable helm of Professor Chris Lidman of the Australian National University, which actually operates the telescope now, even though we in the Commonwealth still own it. What are we doing to protect the night skies? Oh, by the way, can anybody see Brian Cox in that picture? That's in there. Being dwarfed by the telescope when he was visiting to do stargazing live a few years ago. Protecting the night skies of the telescope is very important though. And actually since 1990, we've had legal instruments that guarantee that any developments will have to fulfill certain conditions. The most recent of these were enacted in, or the regulations were enacted in 2016. So we have this 400 kilometer diameter dark sky region centered on the observatory. That's the coast of New South Wales there. Newcastle is somewhere down here. So you get that it's quite a large area. Well, you can tell that because it's 400 kilometers in diameter. But that whole area has various levels of lighting ordinances, which I won't go into. But suffice it to say that we have all of those encapsulated in that document you can see on the left, the Dark Sky Planning Guideline, which is a book that tells you how to do things properly when it comes to putting in external lights. And in fact, they are mandated by law. But that book is the sort of shop window of the legislation. And I think it works quite well. It's published by the Department of Planning and Environment, but we at the observatory put a lot of work into it. So that's fine if you happen to live within that area, then your skies are to some extent protected. But what happens if you're not? If you're a member of the amateur astronomy community, what happens if you're somewhere else? Is there any protection? And I might add that those of you who know me well will know that in my heart, I am still an amateur astronomer. I have been for 65 years now an amateur astronomer, and it still means a lot to me. So this is a question that I take very, very seriously. Well, there are other safeguards, and I don't want to go too much into the detail, but I might just mention these in passing, since these are not to do with satellite mega constellations, but they give you an idea of what protection there is. The Department of Agriculture, Water and Environment, which is now called the Department of Climate Change, Energy, Environment and Water, or DQ, as we seem to be calling it, they, back in 2020, published these light pollution guidelines for wildlife, which are not mandatory in the same way as the dark sky region is around the observatory, but they do actually give guidance on good lighting and how to avoid putting light in the wrong place. There are also national standards, the Australian standards that govern obtrusive lighting and lighting of roads and public spaces. Those are AS 4282 and AS 1158, which are well known to anybody in the good lighting community. I have the again, the privilege of sitting on the two committees that actually regulate those standards. There is a body called the Australasian Dark Sky Alliance, which was founded 4 years ago by my other half, Marnie, which is an advocacy body. It's all about education, good lighting. I sometimes call it gentle activism, because it's activism of a slightly different kind from what we're normally used to. It's what do we want? Moderate change. When do we want it? In due course. So it's that sort of, philosophy, and it works quite well. The ADSA, as it's called, has made quite a big difference in terms of people's knowledge about good and bad lighting. We now have 3 dark sky places, which are designated by the International Dark Sky Association. First one was right next to the National Observatory in the Warrumbungle Mountains. There are 3 more on the way, I'm delighted to say. And at the bottom there, I've made a note of which some of you will know about, because your dark sky site, I'm sure, is part of this. The Astronomical Society of Australia has a designated observatory scheme where observatories that actually do observe the sky for amateur or professional reasons, they are designated, and that feeds actually back into the lighting standards work. So that's keeping the night sky dark. So we move on to chapter 2, which is the daytime sky. Not just the daytime, it's day and night, because to astronomers, radio astronomy is also extremely important. And actually our national investment in radio astronomy is large and spans the continent, from the Parkes antenna in the east, dating back to 1961. It now has a Wiradjuri name as well, Murray-Yang. From Murray-Yang over to the west, where we have the Murchison Radio Astronomy Observatory, which is on Wiradjuri country. That is an entirely different landscape and has different facilities on it. Very briefly, I want to show you some of the instruments at Murchison. There is a precursor to a major new facility that's being built called the Square Kilometre Array, which the department I work in has a lot to do with, which is why I'm showing you the pictures. But the Square Kilometre Array Pathfinder, ASCAP, is what you see in this picture, 36 12-meter antennas. Don't worry about the details, it works mid-frequencies. Those antennas, though, interestingly, are equipped with something like an image sensor, the kind of thing you have in your CCDs, but for radio waves, and that's it on the right there. They're called phased array feeds. That's actually allowing the telescope to look at an image, or to form an image directly, rather than having to scan across the sky. And the other precursor is this extraordinary paddock full of coat hangers, because they're about the size of coat hangers, which is the Murchison Wide Field Array Telescope. It's, as it says there, more than 4,000 dipole antennas spread over the Murchison area. An astonishing instrument, low frequency, but with this enormous field of view. It's a wide field telescope, scanned electronically or steered electronically. And both of those facilities have, as I've said there, been producing outstanding science in the lead up to the Square Kilometre Array itself. And we will host in Australia the low frequency antennas for that. 131,072 Christmas trees in the desert. Extraordinary technology covering that low frequency range. And they are already under construction. This is actually something called the Aperture Array Verification System. It's a test bed for those Christmas tree antennas, but that is going to be the telescope of the future. And because their work on building that is already in progress, you might well ask the question, how do those facilities I've shown you already and the SKA itself, how are they protected from radio frequency interference? There's a lot to say about that, but I'm going to put it very briefly in one slide. There is something a bit like our dark sky region in the optical waveband, but it's split into various zones. The inner zone out to 70 kilometers, as it says there, radio astronomy is the primary user in that zone. And then there are various legislative instruments. The ACMA frequency band plan, ACMA is the the Australian Communications and Media Authority, and they have various licensing conditions as well. I don't want to dwell on that because that's not really what this talk is about. The outer zone, of course, has other layers of protection, and those coordination zones are on the outside. But what I really want to draw your attention to is this. Despite all of this protection that we have for the observatories, for these national facilities, this wonderful infrastructure, there's a new kid on the block, and that's it there. This is an early picture of one of the post-launch sets of satellite trails of the Starlink mega constellation. And the thing about that is it doesn't matter where on the planet you are, you're going to see these things and they're going to affect your astronomy. So that means that our facilities overseas will be affected. Australia has connections with the European Southern Observatory's telescopes at Cerro Paranal, which is what this is showing, where the 4 8.2-meter telescopes of the Very Large Telescope are sited, and at La Silla, I beg your pardon, yes, La Silla Observatory. That's the other one that we have connections with in the European Southern Observatory Australia Strategic Partnership, which, as I've said there, gives Australian astronomers access to these absolutely world-leading facilities. And that's a really interesting partnership. We are already halfway through it, actually, and thinking a lot in the department about how we deal with things when that comes to an end in 2027. And the other overseas telescope that we are really concerned about its well-being in terms of satellite constellations is SKA Mid, the other half of the square kilometre array, which, as you can see there, is situated in the Northern Cape province in South Africa on the High Karoo. 197 of these 13-meter antennas, which is covering the mid-frequency band. So this is where the talk starts. Now, I want to tell you a little bit about this business of satellite constellations with a quote that actually was made by the retiring director of the UN Office of Outer Space Affairs at the conference I was mentioning earlier that I spoke at in February, Simonetta Di Pippo. She said this epic phrase: the introduction of satellite constellations was not trouble-free. And you're dead right there, because it certainly was upset the apple cart of astronomy. So where have we got to with all this? Let me just give you a summary of what the status of affairs is. This diagram, which came yesterday off the Heavens Above website, they have an interactive diagram that shows where Starlink satellites are at any given time. And that's yesterday's snapshot. There are lots of them. How many of them? Well, 2,374 at the moment working. There are a few more than that, a couple of hundred more actually in orbit, but not working. And that is SpaceX's Starlink constellation. They have, in what they call Generation 1, 12,000 satellites approved. Actually, those numbers, as you can see, they're a little bit out of date. They're the most recent I could get, that 2,374. It's probably a bit more than that now. So Starlink is the one that really alerted everybody to the fact that there are a lot of spacecraft going to be up there in orbit. They launch about up to, they haven't done it recently, but up to 120 satellites per month. SpaceX Gen 2 or Starlink Gen 2 is approved already to add another 30,000 satellites to that total. So this is big numbers, and there are other players as well, including OneWeb we have there. Are you showing me something here, Mark, or are you just leaving there because it's rubbish or whatever? Yeah, it's rubbish. Okay, that's good. It's not Mac, so it must be. Other players, OneWeb, a British owned or principally British owned company with 425 working satellites. They've got a smaller number than Starlink planned, but it's still a big number. There's an interesting factoid about OneWeb that you might have heard, because OneWeb, until about 2 months ago, used Russian Soyuz launch vehicles to send their spacecraft into orbit. and the Russian space agency Roscosmos actually took, I think it's 36 of their spacecraft hostage in retaliation for the UK, the UK's reaction to the invasion of Ukraine. It's a complicated geopolitical story, a complicated geopolitical scene. I don't think they got those satellites back, but now actually Elon Musk's SpaceX is going to launch them, which is really interesting because OneWeb is one of his competitors. Very tangled web there. Kuiper is the Amazon organization's proposed web of satellite mega constellations. Viasat is another really interesting one. They hate SpaceX, so there's competition there. A lot of stuff to read about if you ever get the chance. But look at this one. This is really interesting. Last year, the Rwandan government filed an application with the International Telecommunications Union, which I'll say a little bit more about in a minute, to launch and operate 2 mega constellations totaling 327,320 satellites. So far, the Rwandan government has launched 1 satellite, which is a CubeSat. It's the size of a loaf of bread. But they've put that filing in, and that really indicates the sort of, I don't know, perhaps the demeanor of the industry in terms of putting in a bid to grab your bit of space while it's still available, because that's probably all that is. It's an ambit claim by the Rwandan government, who really have not got the wherewithal to launch that number of satellites. So what has caused this activity? And it starts really, and certainly as far as SpaceX is concerned, with technology. I've shown this video clip many times since it came out about 4 years ago. It is astonishing. It is one of Elon Musk's Falcon 9 boosters landing after putting spacecraft into orbit back on a barge with a silly name, as you'll see in a minute, and being returned to Cape Canaveral so it can be used again. That is really staggering technology. They did that first in 2015, but now do it routinely. They've already passed 100 launches with reusable spacecraft. There's the barge with its silly name. Of course, I still love you. I think he's got another one called, if I remember rightly, you might be able to correct me on this, I think it's called Just Read the Instructions. That's the other one. Great names, as you might expect from somebody who's very imaginative. So why is that such a breakthrough? Well, here's a sort of fairly crude diagram of the launch cost per kilogram over the last, getting on for more than 60 years, 62 years. And it's a logarithmic scale. So you can see that the average has been, for many years, it's been about $25,000 US per kilogram. That's the figure I've always had in my head. But then along comes Elon Musk with his reusable spacecraft, and suddenly it drops by a factor of 10. Falcon Heavy can do even better. And if he gets his Starship working, which is the thing that is apparently going to take millions of people to Mars, according to Elon, that is an estimate of what the launch costs will be to get into low Earth orbit, $200 per kilogram. Means I could go for what? I won't do the calculation. Too much information there. But you get the idea. It's the technology that is really driving this. Here's a nice image of one of those boosters coming back. So the ability of SpaceX to reuse their launch vehicles, absolutely dramatic. And then I guess what is really making the push for the mega constellations is that if you put your satellites for communications in low Earth orbit, that means less than 1,000 kilometers above the Earth's surface, rather than at geostationary orbit, which is 36,000 kilometers above the Earth's surface, you get what's called low latency transmission. In other words, you don't get a 3/4 of a second delay as you send the signal out to geostationary and back again. It's coming instantaneously. And that's being driven by, as I've said there, demand for broadband with terabits per second data rates. Guess who the principal drivers of this are? It's gamers. because gamers want to be sitting in one part of the world and talking to others in other parts of the world, and they want instantaneous results. So that's what's providing a lot of the financial backing. And we think, as I said there, that it's been further stimulated by the pandemic. People sit at home and do their thing with either watching Netflix or whatever, or gaming. And then there's the readiness with which filings can be lodged with this organization, the International Telecommunications Union, the ITU, which, as I've noted there, it is the only international regulatory body regulating launches. In fact, what they regulate is spectrum, radio spectrum, as I'll show you in a minute. But basically, they give the tick for launches. And there are zero regulations around orbital congestion. The question at one of the conferences I was at recently was asked of somebody from the ITU, what is the limit to the number of spacecraft that you will allow to go into orbit? And the answer was the laws of physics. In other words, you can crowd up the whole space above the Earth's surface to whatever degree you want, if you're talking about the ITU. But the national regulators sit underneath that, and they then assess the filings. In the US, it's quite complicated. It's NASA, of course, the Federal Aviation Authority, the Federal Communications Commission, and a number of other regulators. We here in Australia have only the Australian Space Agency. So there's a sort of safeguard, but it has to be said that those national agencies tend to be more of a rubber stamp. So really, it's the ITU that is calling the shots. Now, there was a comment from somebody who is very prominent in the satellite industry, Erti Holomaini. She made this comment at the meeting that I mentioned earlier: take those filings with a pinch of salt. And that's exactly what we should do with that Rwandan one, because they're ambit claims. They're people wanting to try and grab the frequency spectrum allocations. And one good thing about the ITU is that if you're a company building satellites, you want to launch your satellites into space, so you put in file a claim with ITU, and then you don't launch them. That gets negated. The claim actually evaporates within a relatively short period. It's probably of order a year. So it may well be that Rwandan claim will evaporate very soon. And I think it's a realistic assessment, as I said there, that the industry itself, the space industry, is concerned about the collision risks associated with these huge satellite numbers. In fact, they're describing it as a space sustainability crisis. Comments have been made that maybe future technology developments will let you get away with fewer spacecraft, although I'm not quite sure how that will work. But, and here's the bottom line, if things progress as we see them progressing now, there could be 100,000 satellites in low Earth orbit by the end of the decade. And that means 5,000 above the horizon at any one time. So as we are sitting in this room, there would be 5,000 above the horizon. You might not be able to see them all, but they would be there. Very interesting prospect. So, well, is that the end of astronomy? Yes, I'm afraid so. I've got to go now. No, of course it's not. Of course it's not the end of astronomy. But it does affect things, definitely. Some footage there from Siding Spring. So thinking first of all about the way the sky will look to our naked eyes. The visual appearance of these satellites is a really interesting thing. The rule of thumb has always been that 100 kilogram satellite in low Earth orbit will be visible to the naked eye. It will have a visual magnitude, we call it V, of less than 7. That means it's visible to the naked eye. Starlink satellites are 2.5 times bigger than that. They're 1/4 of a ton. But since May 2020, and this is all credit to Elon, they've been fitted with these visors, the sun visors that stop the light shining on them. They call them visor sats. Who thinks of these names? And that's an artist's impression of a visor sat there, and the visors are so good you can't actually really see them. That's them, these funny shapes there. These arrows are supposed to show where the sunlight's coming from, I think, something like that. Anyway, that's the style. And the interesting thing is that they actually work. The brightness of a Starlink satellite, when it's on a station at its proper orbit, is down by almost 70% compared with the unvisored versions. So they're only visible to the naked eye when they're actually transferring from launch into their operational orbits, which can take a week, or when they are coming down for re-entry at the end of their working lives, which, by the way, is only 5 years. They have a 5-year lifespan, these Starlink satellites. Good news is that Kuiper is also trialing these sunshades and hopefully will deploy them. And OneWeb, the satellites I mentioned earlier, they are in higher orbits and their visual magnitude is about 1/8, so they're already invisible to the naked eye. And to some extent, I think that addresses the cultural concerns that have been expressed in relation to the changes in the night sky. If you can make it so that most of them are invisible, of course, because they shine by reflected light, then that actually eases the situation. Although, having said that, at any one time, if we've got 5,000 in orbit above the horizon at any one time, then there are going to be 100 of those which are either going up to their orbits or coming down again. I think your microphone battery is running out of steam, Mark. Can I borrow yours? Thank you. Should I try it with that one? Oh, look at that. Talk about an umph. Sorry about that. So yes, it does make a difference. Now, the problem, though, is that it's not the naked eye that's the issue. It's what we see in our telescopes. And this famous image taken from the Blanco telescope down there in Chile, it's a mosaic of, I can't remember how many CCDs, charge coupled devices, making up an image, a wide-angle image of the sky with 19 Starlink trails. This was one of the earliest images that alerted astronomers to the problem back in 2019. And so the problem is most acute for astronomers using wide field imaging telescopes, which is exactly what this is. That's 2.2 degrees, of course, 4 times the diameter of the moon. That's a big field of view. But of course, many amateur astronomers also use these telescopes, so they are at risk from these satellite constellations. Even the Hubble is not immune. Remember, the Hubble's up there at 600 kilometers. They're still having effects from the satellites below them. Up to 8% of images are affected. And NASA has highlighted recently the impact of Generation 2, the 30,000 that are already approved for SpaceX, on what are called PHA searches. What are PHAs? Potentially hazardous asteroids. And that's a line that NASA is taking. You know, you're blinding us to the possibility of finding asteroids that might impact the Earth, of which at the moment we don't know any, within 100 years anyway. One final comment on that is that the facilities that Australian astronomers use are spectroscopic telescopes, both the AAT and the ESO telescopes, and they have lower levels of interference. The radio community, though, has the worst of all worlds. Now, this strange diagram is the spectrum of radio transmissions broken up into all its allocations by the various bodies like the ITU, ranging from a few kilohertz at the top down to 300 gigahertz at the bottom, which is very high frequency. And it's the come on, give me some mic. The one with a circle round there, it's probably my breath that's boiling it off or something like that. Sorry about that. That is radio astronomy. Now, it's hard to tell where it is, but things like that are allocations for radio astronomy. So the spectrum is full of radio transmissions for communications, mostly TV, gaming, whatever, with little segments in between, which is what the radio astronomy community have to use. So you've always got gigantic neighbors on one side of the other, and that's irrespective of satellite transmissions. They have other problems as well. As I've said here, they've got day and night interference, not just nighttime. The satellite beams themselves actually, be pointed, if I can put it that way, directly into the radio telescopes. That affects mid-frequency instruments like ASCAP and SKA mid, the one in South Africa, more than it does the low-frequency ones like the Christmas trees. Yeah, that's right. Christmas trees fall over a bit as well. I hope you're all right, whoever fell off the thing there at the back. I've mentioned this because this is an absolute shocker. Some spacecraft actually beam radar signals down to get height measurements, to get, actually to judge how much ice there is in Antarctica and things of that sort. If you shine one of those into a radio telescope, it doesn't just, doesn't just interfere with your observations. It actually burns the receiver out. Something I hadn't thought of is that many satellites in low Earth orbit are leaky in their own internal electronics. And these radio telescopes are so sensitive, they pick all that up. They pick up the leaky electronics. CubeSats are apparently really bad for that, the ones that are loaf of bread size, because they're built on the cheap and they use really rather poorly defined satellite electronics within them. There are, believe it or not, in spite of everything I've told you, there are unregistered satellites. Something like 15% of all satellites in low Earth orbit are apparently unregistered. That's excluding the military ones. And so they're a problem too. And certainly in terms of what's going on in Western Australia, in the desert there, if you've got 5,000 satellites above the horizon at any one time, they're going to reflect back the VHF FM transmissions from cities like Perth or Geraldton. It's a really bad news situation. So what are astronomers doing? Well, they started off by doing a lot of grumbling, as you might expect. And I think there's an interesting psychological point here, because there's no doubt that astronomers for probably about, well, certainly the 400 years since the telescope was evolved, perhaps, rather than was invented. Since in the 400 years that they've been using telescopes, astronomers, I think, have gone around with very much a sense of entitlement about the night sky. Well, we're the only people interested in it. Whereas now, suddenly, other folk are interested in it too, and that is not so much a shock to the system, but it's something that needs care and attention. So that care and attention was, as you can see there, many, many conferences and workshops. There is going to be a focus meeting at the International Astronomical Union General Assembly in Seoul in next month. In fact, it's entitled Towards a World Standard for Dark and Quiet Sky Protection. The quiet, of course, refers to radio quietness, to signals, an absence of radio signals. Various technical papers. So COPUOS is the Committee on the Peaceful Uses of Outer Space, which is the body that I was speaking at in February. And IAU have made draft submissions, but this seems like a small step, but it was a giant thing at the meeting, and we didn't think it would get through. But dark and quiet skies are now on their next year's agenda, because it's not automatic that a topic like this would go from one year to another. So the UN will discuss it again. It keeps it on the horizon. And I mentioned the NASA concern about Generation 2 and their the possibility of missing potentially hazardous asteroids. They wrote a pretty strong letter to the Federal Communications Commission back in February. So I'm nearly winding up, so if you're all freezing, it's not going to last much longer. But there are opportunities. We can't let this just go by and hang our heads and say, well, that's the end of astronomy, let's all go to the pub or whatever. There's more to be gained from this. And so what's happening is a number of things. First of all, you've got to ask the question, what do astronomers actually want the space industry to do? And I should mention, sorry, I meant to say this before, certainly here in Australia, we have a space agency, which is the department I work in, that is is conflicted because they are very industry focused. They want to encourage the use of space. We're all using space all the time, even though most of us don't know we are. But they also are part of a department that is putting significant financial support into major infrastructure for astronomy. So there are two conflicting demands here, and it's tiptoeing your way through that, which is what we have to do, and what astronomers want from the space industry and what the space industry might want from astronomers. So here are some of this is the wish list. Minimize satellite numbers, well, that will be very nice, but more critically, if you put them below 600 kilometers, then as this diagram shows, I don't really have time to describe it, it's a worst case scenario. It's what happens at the summer solstice if you've got 10,000 satellites at 1,000 kilometers high and 500 kilometers, and I guess you can get the idea that they're non-visible during the middle of the night if your satellites are at lower altitudes. If they're high, they are visible throughout the night. And of course, OneWeb is up there, although there aren't as many as 10,000. There will only be a few thousand of those. So it's good news that SpaceX actually complies with that too. They have come to the party on that one since April 2020. We need a way of making sure these spacecraft don't directly illuminate radio observatories, and that's a possibility. Also, that the industry should comply with the regulations, the International Telecommunications Union frequencies and flux, the amount of radio signal that there is. Sometimes operators don't actually take notes of that, and they go over the top or they leak into the radio astronomy waveband with their transmissions. So if there was good compliance, that would help. And, well, better regulation generally, because at the moment, there's none that relates to optical astronomy, and it's limited for radio. And one of the other things that's important is if you can tell people, and by people I mean anybody, whether they're astronomers, amateur astronomers, anybody with an interest in where these spacecraft are, if you can tell them where your spacecraft are, then you've got a good asset for people who want to avoid them and want to make sure their telescopes aren't looking in that direction. So very briefly, and I do apologize, I am over time, but the latest thing is this IAU Center, the Astronomical Union Center. It's a gobbledygook name. We usually just call it the CPS. It's being hosted by two organizations. SKAO is the Square Kilometer Array Observatory. NOIR Lab is the US National Optical and Infrared Laboratory. It used to be called the Optical Observatories. That center has now been founded. They kicked off on the 1st of April. I had a pleasure of talking to a couple of weeks ago to some of the people from SKAO about it, and they're very happy with the way it's gone because they started off by listening to the communities, all the communities, and now have a much better idea of where they want to go. It's really a coordination body. They'll coordinate the efforts of the astronomical community, as it says there, acts as a bridge between all stakeholders, and that includes amateur astronomers and individual hobby astronomers. Continue research and disseminate resources. And I've just somehow managed to get rid of my screen there. 4 core areas. I won't go into the detail of that. You can find it all on their website, and I'll give you the address of that in a minute. And my comment on this is that the key to success is really engagement between industry and the community in formulating effective mitigation strategies. What that means is allowing astronomers to have some say into the design of the spacecraft before you launch them. And actually, the industry is open to that. You might see SatHub mentioned there. What is SatHub? It's a proposal that was put forward by one of the working groups for the kind of things that might be useful for taking this forward, these opportunities I mentioned. Astronomical data repositories, orbital solution portals, all about where the position of the spacecraft are, and various software tools, training, and real-time collaboration. And finally, almost my last slide, not quite. Have any of you seen that? The string of pearls effect of, there's one hand up, yeah, where one of the Starlink Falcon 9 launch vehicles starts spitting out the 64 or up to 64 spacecraft that it has. You get this string of lights going across the sky. and oops, I've done it again. Sorry, I must stop pressing that button. Opportunities in the wider community. So it plays into outreach. My view of this is very strongly that we can use that. Sightings of string of pearls effect feed directly into outreach opportunities. People don't have, generally speaking, have no idea what they are, and they do want to know. Often it's aliens, or something happening. Maybe Mr. Putin has finally sent something across that we didn't really want. So people are full of wild ideas, and I think once they understand what's going on here, they do understand the consequences for astronomers, and I think that lends to a sympathetic hearing that then would allow you to open up astronomy outreach channels, perhaps more widely. I think that at very least what it does is focuses people's attention on the night sky, and that's always a good thing for astronomy. Something else I might note there is the IAU Centre is keen to communicate with science communicators, no matter what level they operate at, and there will be good outreach materials. They're still only 3 months old, but that address there, cps.iau.org, takes you straight to their website, which is still a work in progress. But I think we're going to get good stuff from them because they've got the finger on the pulse generally. And finally, if you're a serious amateur astronomer, these SAT-hub type algorithms will very quickly become available, probably commercially, which will allow, if you're keen on astrophotography or occultation timings, variable star observations, supernova searches, or even exoplanet transits, which amateur astronomers contribute to now, they will help to make the job easier. You've got a job that is not as easy as it used to be because things like trail mask, which is masking the trail of a satellite through an exposure, or pass predict, telling you you've got to stop observing now because there's going to be a Starlink satellite passing through your field of view. That's nowhere near as easy as it used to be, but it is still possible, and astronomy can still thrive. And so my bottom line in the talk is astronomy won't be the same. If we get 100,000 spacecraft in orbit by the end of the decade, it will not be the same. But my take on it is that it will still be fun. You'll just have to work a bit harder. That is the end of my talk. Thank you very much, everybody. I'm sorry it's got so late, but I do appreciate your hearing. Can I go home now?
It's working. It's working. Yes. No, you can't go yet.
All right. Okay.
People might have questions. Do we have anybody who has a question? I think you've scared them all away from.
I know. I scared myself there. I can tell you.
Oh, we got a question. And while you're answering that question, I'll throw your Mac away.
Thank you.
Plug the other computer in.
From one Mac owner to another. So I approve. No, actually, mine's a very simple one, just down to grassroots with respect to local councils and their take on just lighting. They always use the same Australian standards. But are they going to try and embody some standards we're doing, in those zones in just general council areas, just generally as we move forward?
Yeah, that's a great question, actually. And that's one of the things that the ADSA, the Australasian Dark Sky Alliance, is very keen on. And I guess I can give you the statistics on this because they're quite close to home. Probably at least once a month, there will be an inquiry from a local council asking how they can improve their control of urban lighting. I think partly that's because they see, first of all, they see dark sky parks, which are actually good tourist attractors, but they also see the lighting standards just gradually tightening up a bit on upward light spill, and that those things together actually lead councils into thinking, well, we better do something about this. They might be being dragged kicking and screaming into it, but some of them are actually quite enthusiastic. So it is happening. Awareness is great, absolutely.
Oh, we have one more question. I got down the stairs for no reason then.
Go and hold the mic to him.
When you use satellites for internet,
Yeah.
It's dramatically further to go up and then come back down. But if you're going overseas, it must be grotesquely slower. So the question I'm asking is, except for remote communities, where's the benefit in having that huge satellite obstruction?
Yeah, so that's the thing. These things are only, 500 kilometers up. So it's a very short path length. They talk to each other. And yes, it's still got latency, but it's nothing like what you get with geostationary. So it's not that big a deal. I mean, remember, light goes around the Earth 7 times in a second. So even if you were going all the way around. But the other thing, though, is that you put your finger on something I forgot to mention, and that is for remote areas, for mobile facilities like ambulances on the move. This low latency internet is an absolute asset. Remote areas, we've got plenty of them in Australia. Actually, Starlink now already has 400,000 subscribers. The thing is taking off, even though they've only got a third of their spacecraft currently in orbit. And just one sort of slightly offside, but I think very valuable answer to why you want to do it is Elon Musk made Starlink available to Ukraine as a whole when the conventional things were being blocked. So it does have its uses, and that's the issue. We as astronomers can easily say we don't want all that rubbish, but there is this very wide section, and it will grow, of the community that wants exactly the facilities that they provide. It does, but you're still talking about a small fraction of a second compared with the alternative, which is geostationary. Fiber networks, they require infrastructure that I think has been compared with space infrastructure. The fact that, first of all, let's not beat about the bush, Elon Musk is a very unusual person. I'll stop there with my assessment of his character, and probably has more interest in reducing the cost of space flight than getting mixed up with fiber cables under the sea. Maybe the correct answer to your question, which is well-founded, is that there's room for both. That might well be the bottom line there. Thank you very much for it. Yeah.
We're one of those 400,000 at the ASV.
Are you?
Yeah.
Do you like it?
At LMDSS, we love it, yes.
Yeah. Everybody says.
It's evil, but it actually does us.
Yeah. Yeah.
We're in bed with the enemy. Yeah.
I was going to say, are you going to vote him off from being the ASV president?
That wasn't in my term. I did. I'll blame the previous.
What a cop out! What a cop out! Anyway, yeah. Look, it's what people say. People say it's terrific.
It is. It helps us live stream our events from the dark sky side.
There you go.
Helps radio astronomers send their data around. Helps everybody upload their fantastic astrophotography images.
Yes. So what a hard sell.
I know.
Is Elon paying you?
Maybe. No. I wish. I don't have a Tesla in my driveway yet.
Yeah. When you come up, when he turns up in a Tesla, then you know. You know whose pocket is in.
Well, thank you very much, Fred, for coming to our talk tonight.
It's always a privilege and a great pleasure to see you all. Thank you.
Oh, no. Oh, there it is. It's back. Don't run away yet. I'd love your assistance. I'm going to get somebody else's assistance as well. But we have 2 prizes to draw for our raffle, which we've been running. So it's not a very hard job. But if you'd love to push the mouse button so we can draw our first winner, just press down on the middle bit and that'll be it.
Hang on, am I spinning
Actually,
it?
I might have to click the little button down.
Oh,
there.
sorry.
No, the big one, the one above.
I need to put my glasses on.
It's not hard. It's not hard. It's really, come on. This one here. That's
that
it.
one. All right, I'm pushing.
Push it and let it go.
I see. That's the bit you didn't tell me. Spinning.
Who's going to win? Who's going to win? We have 2 of these too. So this is the first one. We don't want to save the image. We want to know who won. Wayne Woolston.
Oh, that's the best raffle I've ever seen.
That's cool, isn't it? It's a spinning wheel. It's a wheel of names. Yes. Thank you very much for that, Fred.
It's a pleasure.
We'll get you back up on stage in a second with the others as well. But I want to get Bill Stent, the telescope gent. from Sidereal Trading, who has sponsored this raffle with some tripods, to come and draw the other one. So we'll make contact with Wayne. We'll escape out of that. We'll remove one of Wayne's entries because we don't want him to win again. And Mr. Telescope Man, who works for the company, who graciously gave us the tripods that go with these Star Adventurers that we're giving away with the raffle. If you can press the button there, this button here. Yeah, see if you're a better student. That's it. Press it and let it go. And we're spinning. It's pretty boring, isn't it? Waiting. Who's got this one? It's not Gavin, is it? Peter Duncan. There we go. We'll make contact with Wayne and Peter. I'm pretty sure Wayne has actually won a prize before. I'm not sure. I think he might have. Well, there you go. That's our raffle draw for the 100th anniversary Astro Talk. Now, I'd like to thank everyone who has been involved in the society over its 100 years. I'm sure those members prior to us and now have enjoyed sharing our knowledge of the universe, and we hope to share it for 100 years or more. Special thanks goes to our three guests, Sara Webb, Claire Kenyon, and Fred Watson. Thank you very much for coming along tonight. 3 wonderful talks. I hope everybody enjoyed the talk, and we will see you next month at Mueller Hall. And for those watching at home, hit the like button, press the bell, all the fancy YouTube and Facebook stuff. And if you're on Twitch, we're on there as well. We'll see you next month.